Good afternoon, everyone. On behalf of all of us at the National Glass Association, thank you for making time in your day to join us for today's Thirsty Thursday. It features a topic we're receiving questions from all angles and stakeholders on, embodied and operational carbon. So we're glad you're here. The NGA Glass Conference Chicago is just over 2 weeks away. It's not too late to register, and we've got some fun things planned. In addition to facility tours and happy hours, some topics on the agenda will include edge grinding, backstops and how they affect the industry, active shooter standards, and the usual technical and codes updates. Visit glass.org to learn more and to register. Glass Build America is happening October 18th to 20th in Las Vegas. Registration is open, and so be one of the first people with your name on the list. Better yet, send us a selfie video answering the question, I go to Glass Build America too. You may be featured in a social media promotional video montage. I'm now pleased to introduce our speaker. Dr. Kayla Natividad is an architectural technical service engineer for Pilkington, North America. She received her PhD in civil engineering with a focus in structures and glass design from Texas Tech University. Since joining Pilkington, North America, a major focus of her work has been in sustainability and green building design. Kayla has and continues to promote green building initiatives through education and advocacy of glass technology. Kayla, welcome.
Thanks, Sarah, and thank you, NGA, for allowing me to speak today and everybody for attending. Hopefully by the end of this, you're able to take away some new information or spark some new discussion around embodied and operational carbon in design. So before jumping straight into discussions on the carbon impacts of glazing, I really want to take a minute to address what's driving discussion around design and climate change and why we keep hearing these buzzwords of embodied carbon, operational carbon. And so really when we talk about building design, material impacts, or even energy codes, we often hear it framed from the perspective of sustainability. Architects strive for sustainable designs, manufacturers offer sustainable solutions, but it had me thinking, and I want to take a step back to see what the definition of sustainability was. And from that dive, I started thinking we should really start also introducing the concept of resiliency. So in Black, you'll see the definitions from the United States on sustainability and resiliency, but I've put them into more simple terms. Sustainability is essentially just protecting the environment from human impacts. That's why when we talk sustainability, we're talking about reducing energy use and in turn reducing our carbon emissions or global warming potential. Alternatively, resiliency is protecting humans from environmental impacts, so potentially impacts that have already occurred and how it's changing the way we design. And so whenever we start talking sustainable design, I really think maybe we should start talking about designing for both and not necessarily just a sustainability mindset. And really why this is important is because more than half of US commercial buildings were built before the year 2000. And as energy codes develop and change, they definitely don't meet some of the more efficient codes today. So what may have been sustainable yesterday isn't necessarily resilient today. And here I've included a few recent articles, partially for dramatic effect, but mostly because they're really relevant depictions of change and impacts that have occurred even in the last couple of years. And we're seeing some more starting this summer with regard to, heat, with regard to really hot temperatures further north. And so I think this alone is reason enough to start talking both sustainability and resiliency. So how does what we do really impact sustainability and resiliency of our communities? Well, if you've attended any presentations on carbon impacts, I'm sure you've seen at least the top two statistics on here. But buildings account for almost 40% of global CO2 emissions. And from that, we can go on to say 80% of buildings that will exist today or that will exist in 2050 already exists today. So I'm going to pull the statistic from the last slide, and through rough analysis, we can assume that that means about 40% of the buildings that will exist in 2050 were built before the year 2000. Now we think, okay, well, from a glass design perspective, IGUs were introduced in roughly the 80s, encoded IGUs. And so anything built before 1980 is likely still monolithic, or if it's an IGU, it's probably an uncoded IGU. So we know that in the last 20 to 50 years, we've made leaps and bounds in our coating performance and glazing performance. And we know what we're capable of doing for new construction today, but we have to find a way to apply that to existing structures to really narrow down on what this is. Existing buildings account for over 65% of New York City emissions. And so that's pretty significant for a large city that has a lot of glass. And if there's a way that improving your facade, and we could go through and find a way to improve those buildings' efficiencies, then we can help reduce the amount of emissions coming from existing buildings. So with all that, where do buildings come into play? Like, where does all the CO2 emissions in a building come from? Well, that can be broken up into two separate sections. It's embodied carbon and building operations. I did a lot of really deep diving research and now am an expert on bodybuilding, but not really. I did find a way to make this comparison though. So we could think of embodied carbon as our bulking. Essentially, any new material you include on the project, any new mass you're introducing is increasing your embodied carbon of your building. This is essentially, if you are making or if you're using an existing building, you already have the embodied carbon of your existing building there. So really, your introduction of new building materials is going to be pretty minimal as compared to a new construction. So the most efficient, the most environmentally friendly building is a building that already exists. From that perspective, all of your design materials that you introduce really will impact your building operations, which is your cutting season. Really, what you're trying to do is you're trying to introduce healthy building materials that will in turn create energy savings on your operations front. So building operations can be seen as cutting season. That's whenever you're really making all your savings and essentially seeing if what you introduced into the building or the new materials you designed for are giving you the performance that you wanted. So we have to be mindful of what we're taking in with regard to our embodied carbon and how it affects our end results, which is our building operations. So how do we go through and really take in, how do we design for clean or low embodied carbon? There's two different solutions. The first one is everyone's looking at EPDs, environmental product declarations. What this is it tells you your global warming impact of a material, essentially based from the manufacturing process. So on the left, you'll see here, what it covers is your extraction of raw materials, the transport of those materials to your factory, and the actual energy and carbon it takes to manufacture that product. It doesn't include transport to the site, construction of the building. It also doesn't include any recycling. It could include recycling prior, but usually doesn't. And so essentially your EPD is going to be covering what's circled in orange. And essentially all of the gray portion there is going to be your operational performance. So you can look at a material's EPD and see what sort of environmental impact it's making. And there are ways that manufacturers are looking to reduce their global warming potential or their embodied carbon of their products. In the glass industry, some of these ways are introducing hydrogen or alternative fuels to fire the furnaces. We're also seeing a strive to use more recycled glass, or what we call a cullet. As you start introducing more cullet into your batch, you require less energy to melt your raw materials. And essentially you're able to generate or produce glass with less energy and less carbon emissions. Another thing we're looking at is introducing renewable energy. So glass making, the flow process is very natural gas intensive, but there are a lot of aspects outside of the furnace itself that still use some significant energy, such as our like packing stations, or essentially the things that aren't running on need to be extremely heated on the cold end of the line. And so there's introduction of renewable energy to help offset some of that energy use. And lastly, you'll see is a lot of manufacturers using carbon reduction targets. So essentially promising to reduce their emissions by a certain percentage, usually by 2030 or 2050 or where you see those goals. But since a float line is built to last for a significant long time, we'll say approximately 20 years, it would take a long time for these solutions to come into effect. And with the way that things are going, we need solutions now. So right now, the fastest way that we can impact our embodied carbon and our operational carbon is through our facade design. So like I said, embodied carbon is essentially the carbon emissions from all of your raw materials. Here's a nice example I like using of the watermelon. You see the interior, when you look at the way the watermelon is structured, the interior of it can be considered the structural elements. So that's your concrete, your steel, your potentially mass timber. That's really where the largest mass and volume of new construction really is. And so glass covers a large surface area similar to the rind of the watermelon, but it really is a small portion of the installed total mass or volume of the building material. And so this is why we say the building that already exists is probably the most sustainable building because you don't have to reintroduce all of these new structural elements typically. And the idea is to reduce the new materials that are being used. And like we said, we want to reduce the new materials being used, but we also want to make sure that you're able to get some sort of payback. And so we want to improve the operational performance with these new materials by allowing them to reduce the energy use. So how do we do that with glass? Well, typically glass performance is broken down into these main three factors: your U factor, your solar heat gain, and your visible light transmission. U factor and solar heat gain are typically for thermal and solar comfort to improve occupant comfort, reduce your HVAC load requirements, potentially improve building resiliency by improving the insulation of your design. And visible light transmission is more for aesthetics, so improving your quality of views. You can reduce your need for artificial lighting, which can reduce your energy load, and you can improve occupant health and productivity through high day lighting. When we see how this is addressed across the country, there's not really a one size fits all. I'll go through and show some examples of how glazing can impact building performance across where all of these stars are. But essentially the idea is in hot climates, you have really hot summers, you don't have as hot of winter or as cold of winter. So you really want to reduce your solar heat gain. And that's where the focus is in hot climates. But in colder climates, as you move up north, you want to allow that passive solar to help in the winter, and you want to better insulate. So you're not losing any of your heating in the winter. But from what we saw earlier, designing for resiliency, that's not always the case today. There are some areas that we're starting to see significantly colder winters in the south and significantly hotter summers in the north. And so now we have to start thinking where we find that balance of solar heat gain and U factor in sustainable design moving forward. So strictly talking existing buildings, we want to think, what is the design approach that we should be using? And to steal the old reduce, reuse, recycle, I want to introduce the reuse, reduce, rethink. So reuse existing building materials that you have, use existing buildings. Potentially, if you can use an existing sash, if you don't have to introduce new metal or structural elements, that would highly benefit your embodied carbon take. You also want to reduce the amount of new material, and you want to rethink of what glazing can do, and we'll get further into that. So just to start with, through embodied carbon reduction, to reuse materials, one of the new materials that we're looking at is vacuum insulating glazing. This is a typically 6 to 10 millimeter glass that fits in existing monolithic sashes. So like I said, anything made prior to 1980 still likely has some monolithic glazing in it. When you look at the embodied carbon breakdown of new windows, most of the embodied carbon contributions come from your framing elements. So if you're able to reuse your existing framing, you're significantly reducing the additional embodied carbon that you're introducing. There are trade-offs. So usually if it's a monolithic existing sash, you're not going to have those thermal breaks in there. Or it may not be a material, or it may be a material that's more conductive. But really, this is a project by project basis on how you should evaluate that. But with regard to vacuum insulating glazing, what you're able to do is you're able to get a typical IGU performance, so a 1-inch IGU performance in a monolithic form factor. So you're not introducing additional weight, allowing or needing more reinforcement. You can reuse your existing sash, and you can maintain potential operability of your existing sash. And so using Energy Plus and LBNL window, we did a quick small office building energy impact analysis across all of the climate zones that I showed and seen before. And what we see is as you go through, well, in the first, you have just a typical 6 millimeter clear of what would be installed. And we went through and introduced 2 different VIGs, one with a pyrolytic low E in it, the other with a sputter low E on surface 2. And you see, as you start improving your product performance, you're able to go through and reduce your cooling loads and your heating loads, significantly improving the operational energy or operational carbon of your structure. Another thing that we're seeing with regard to existing buildings is the addition of secondary window systems. Most people think, oh, it's just an interior exterior storm window. A lot of people use just a sheet of clear monolithic glass, but now that we have thin solutions that have higher energy performance, you're able to use some of these high performance glazing solutions in addition to your existing glazing to reduce your operational carbon by improving either your U factor, solar heat gain, or both. There are interior and exterior solutions. All lightweight can be glazed on site. One of the most popular buildings that has had this installed was the Empire State Building, and I believe it was Alpen High Performance Windows introduced a interior storm window on those. And so there are benefits with regards to energy performance, and you can quickly make up the embodied carbon from your energy savings. But the drawback is there is potential to lose operability if you are covering operable windows. So here's another, did a similar small office building energy impact to show this. And you see in the first light is our typical 6 millimeter, or in the first column is our 6 millimeter clear monolithic. And as we move along, it's with the addition of a clear interior storm with a surface 3 low E, and then an interior storm with a VIG. And so you'll see the significant savings that you're getting as you start to improve what you're using as your storm window. And by using lightweight or thin high performance materials as a storm, you significantly improve your building performance, and you're able to make up for that embodied carbon of these additions. Now, talking embodied carbon reduction, there are structures that have IGUs right now, existing buildings that have IGUs. So going through and replacing them with a monolithic form factor wouldn't really make sense. But you still want to make the improvements. And so one thing we can do is now with the adoption of the thin triple IGU. So it's the same form factor as a typical double IGU, but it now has a thin center light. So you can improve your operational performance. And the thin center light reduces your embodied carbon impacts. One, because it can fit in a standard double IGU system with a similar weight when compared to a traditional triple. And with the way embodied carbon is calculated, the thinner your glass is, the less embodied carbon your material has. And so we know triples have been introduced for a while now, but you can see on this bottom chart that really predominantly what we're using is our double low E IGUs, and triples really haven't taken off. This is residential, but I think it's safe to assume that our other markets are very similar. So it's just something to consider whenever you're going through and looking at renovating an existing double IGU sash. And lastly is the carbon reduction, rethinking what glass can do. So with the introduction of transparent photovoltaics, I borrowed this image from Ubiquitous Energy, but the idea is that now instead of it just being a passive insulation and essentially weather barrier for your building, you can have a dynamic window area that's actively giving you or producing energy and improving your embodied energy payback for a net zero building performance. And so essentially now, rather than only dealing with your rooftop, you can have a vertical solar farm. This is really just an overview I borrowed from Steve Selkowitz on where the market is today and what we're seeing, where the market is going. And I think it's going there in both new construction but I think we really need to apply it into existing buildings, which is thin triples, vacuum low E's, hybrid VIGs, and potentially aerogels moving forward. And to tie back in some of this we were talking about resiliency, and what does any of this have to do with resiliency? Here's just an example of what an interior temperature of a building would look like during a winter power outage. So there's two different types of building. You have a single house family, which is a smallish structure you can have in an all glass high rise. So you'll see from the dotted lines, this is essentially your interior temperature during a winter blackout as your days progress, and your solid lines are what a high performance glazing system would do, acting as your passive facade support. And so you can maintain significant, you could maintain your interior temperatures and really improve your resiliency and your occupant comfort through any of these time periods. And so with that, really the big takeaway on this is for existing buildings, we want to minimize additional embodied carbon impacts by using existing buildings, and also really take the time to improve our operational performance, because by improving our envelope, we allow for resiliency, we allow for operational energy reductions, potentially lead to smaller HVAC systems or less reliance on your HVAC system in general. But in new construction, there's a wide variety of available technologies. Really, the sky's the limit on that. So what we want to take into consideration is more designing for the future and making sure that whatever your design is, you're able to get that operational savings. You're able to get your operational savings to have a fast turnaround over and make up for whatever the embodied carbon you put in initially. I know I spoke really fast, and channel in, but I hope you're able to take something from this. So thank you all for attending. And if there are any questions, I'd be happy to field them.
Yeah, thank you, Kayla. We've gotten one in the Q&A so far, so let's address that one and then we'll see if anything else comes in. If you look at the total carbon of using BIG, is there actually a benefit for using it? And same question for BIPV, the comment being the carbon cost to create BIG or BIPV for low efficiency on a vertical wall may or may not have the payback that people are seeking.
Yeah, so I think whenever we talk payback, so there are two different ways we think about it. If it's financial payback, I really can't answer that. It's a hard question to answer. But when we start talking carbon payback, we actually did a project in Detroit where we were able to reglaze what was existing monolithic clear glass. And we replaced all the lights with VIG, and we were able to see that there was a carbon payback with regards to our operational energy savings and what it took to make your VIGs of about 3 months. So it's a really fast turnaround, but I think really the kicker is because we were able to reuse your existing sash. And you get such a significant increase in your operational performance and your operational loads that that turnaround is actually really quick. And we see the same thing. I believe Tom Culp did a paper on thin triples, and if the addition of a third light would really make sense with regards to carbon payback in residential. And we saw that it was a similar turnaround of, I think the carbon payback was about a month. And so, yeah, I think the carbon paybacks absolutely is beneficial. You're right that it is high embodied carbon with regards to if both lights are tempered or if they're laminated. But when you look at really what the impact of what that's having on your building performance, that the carbon payback is it's an easy story. It's a no-brainer.
Okay, great. Another question, what is the embodied carbon of glass compared to other facade materials? Should we design with less glass and lower window to wall ratio?
Yeah, so I will say whenever you look at the actual number per volume, I guess per ton, the global warming potential of glass is a bit higher. But when you look at the way that the amount of surface area that's covered compared to other building materials, we cover a lot more area with a lot less material. And that's just with the way that we're designing. I mean, we're dealing with even a double IGU still only has 12 millimeters worth of glass as compared to other facade or wall systems. And like I said earlier, you really see the highest impact in your concrete and steel, just based on global warming potential by volume. So I don't think designing with less glass and lower window wall ratio is really the solution, because now even though you're not using the embodied carbon of whatever the glass is covering, you're actually introducing more by volume from your other building materials. So I don't know if that answered. I hope I answered that.
Great, thank you. Another question, how do the different configurations perform for sound reduction?
Yeah, so I think it depends on which configuration you're really looking at. But if you look at any of the ones I talked about today as compared to the monolithic that they would be replacing, I mean, you're going to get better performance just because once you start introducing more mass, more airspace, or even potentially laminate in there, you start improving your sound performance or your sound attenuation of your design. So really, I think right now, a lot of what we see with regards to storm windows is used for improved sound performance. And that now we just have to add on the additional benefits of using better glass in your storm windows for better energy performance.
Awesome. Okay, we have another one just came in. Do you believe just replacing glass in existing buildings is enough to reduce the environmental impact to an acceptable limit, or is it just the starting point?
No, I think it's just a starting point, really. You know, it's not a one quick answer for everything. But I think by replacing the glass and improving your facade, what you're doing is you are impacting that building performance, and you're introducing resiliency in case of your power outages. And that's really where you want to start, because by improving your building performance from your facade, you're able to then go into your HVAC systems and really optimize those designs. Additionally, one of the easiest hitters is just improving your lighting. So much of an energy's building use comes from lighting alone. Whether you're moving to LEDs or you're moving to even just, you know, self timers. A lot of buildings are starting to use timers to really just optimize how efficiently they're using their energy. And I think you're improving your facade is just the starting point.
Okay, excellent. Not seeing any additional questions. We will wrap today's presentation up, but we hope you enjoyed it. And again, if you have questions that continue to come to mind, Caleb, I guess you're welcome or open to receiving inquiries directly via your email address on the screen. Kayla, thank you for your time and expertise today. And again, to everybody for joining us. And we hope to see you again at a future NGA event. Have a good afternoon.
Thank you all.